Thus far, we have talked about two of our modified divisor apportionment methods. In this video, we're going to look at Webster's method, or we're going to start with Webster's method. And in Webster's method, it is very similar to both Jefferson and Adams' method, except that Jefferson awarded the lower quota always, Adams awarded the upper quota always, and Webster's method is actually going to use conventional mathematical rounding to decide whether to round up or down. So with Jefferson, you always rounded down. With Adams, you always rounded up. And with Webster's, you're going to round according to conventional methods. So our process is still going to be to find that modified divisor and to use it to find the modified quotas, and then to assign the apportionment based on whether or not you should round up or round down. So let's look at our same example. We still have the Interplanetary Federation of Fraternia. They're still trying to award the 175 seats. And in order to find our standard quotas, we first have to find the total population, use that to find the standard divisor, and then find the standard quotas by taking the population of each state and dividing by the standard divisor. And you'll notice that that process was the same for Jefferson, Adams, and Webster's method. Where they differ is in this initial apportionment. Jefferson always gave the lower quota, Adams always gives the upper quota, but Webster's is going to use conventional rounding. And remember, we're rounding to the nearest whole, so we're always going to look at this digit that's in the 10th place, or the first decimal place. And if that is 5 or higher, then we're going to award the upper quota, or round up. If it is 4 or lower, we're going to award the lower quota, or round down. So for A, we're going to round up to 20. For B, we'll round down to 14. For C, we will round up to 68. For D, we will round down to 26. E rounds down to 18, and F rounds down to 29. And you can see that our initial apportionment did in fact apportion 175 seats, which is exactly what we were looking for, and therefore we are done. We don't even need to choose a modified divisor in this case because we had the correct number of apportionments initially. And that's one of the beauties of Webster's method that's never going to happen with Jefferson or Adams, and that is that Webster's will sometimes give you the correct apportionment in the initial apportionment. Whereas since Jefferson always awards the lower quota, Jefferson's is always going to be too low initially. Since Adams always awards the upper quota, Adams is always going to be too high initially. So with both of those methods, you're going to be required to do a modified divisor. Whereas Webster's, you might be required to do a modified divisor, but in some cases, you will get the correct apportionment initially. So that's kind of the positive of Webster's method. So an advantage is it applies the same formula to all states. It's population neutral. So in other words, it's not biased toward large or smaller states, and it doesn't produce any paradoxes. However, it can violate the quota rule because both upper and lower quota violations can occur. However, they are very rare for Webster's method. So Webster's method is actually a pretty good method, but it turns out it's not the best method. There's actually one method that has less flaws than even Webster's. And that brings us to our final apportionment or modified divisor apportionment method, which is the Huntington-Hill method. In the Huntington-Hill method, our goal is still to change the modified or make a modified divisor or find a modified divisor, so that when the quotas are rounded based on the geometric mean, there is no deficit or surplus. So Jefferson rounded up, Adams rounded down, Webster's rounded conventionally, but Huntington-Hill is going to round based on the geometric mean. And you've probably never heard that term before, and that's okay. We're going to talk about what it means and how we're going to use it. But it's just important to understand that that's what we're going to use to decide whether or not we are going to award an upper or a lower quota for each state. So you'll notice our steps are still very much the same as the previous examples. We want to find a modified divisor. Use that modified divisor to find each, that should be states, I'm sorry, not stats, modified quota. And then we're going to assign each state its rounded quota based on the geometric mean. If we do not get the apportionment we're looking for, we're going to go back to step 1, try a new divisor, find new modified quotas, and award again. And we'll repeat that process until we do find the apportionment that we're looking for. So in order to use the Huntington-Hill method, we have to understand how Huntington-Hill rounds. And it rounds based on the geometric mean of the two numbers. And so the two numbers that we're working with here are going to be the upper and the lower quota. So the geometric mean of A and B is simply the square root of A times B. And then we're going to use that geometric mean to round either up or down for our Huntington-Hill apportionment method. So the rounding is based on the geometric mean. If the quota is greater than the geometric mean, then we're going to round up or award the upper quota. If the quota for the state is less than the geometric mean, then we will round down or award the state its lower quota. So let's round the standard quota of 4.471 based on the geometric mean. Well, the first thing that we have to do is find the geometric mean. And remember that the geometric mean is the square root of the lower quota times the upper quota. So since 4.471 has a lower quota of 4 and an upper quota of 5, its geometric mean would be the square root of 4 times 5, or approximately 4.472. Now, let's compare this standard quota, 4.471, to its geometric mean of 4.472. Is 4.471 higher or lower than 4.472? Well, remember, when we're comparing decimals, we have to compare the numbers that are in the same place values. So 4 and 4 are the same. 4 and 4 are the same. 7 and 7 are the same. But 1 is smaller than or less than 2, so the standard quota is less than or smaller than the geometric mean, and therefore we are going to round down or award the lower quota. What about the standard quota of 4.473? Well, notice that that still has the same geometric mean because the lower quota of this number would be 4 and the upper quota would be 5. So this is the same geometric mean. But in this case, because the 3 is greater than the 2, then the standard quota is greater than the geometric mean, and therefore we would round up to 5. So when you're using the Huntington-Hill method, you must first find the geometric mean and then compare the standard quota or the modified quota, whatever quota you're using, to the geometric mean, and always in that direction. So it's always, is the quota higher or lower than the geometric mean? Because if you do it backwards, if you say, is the geometric mean higher or lower than the quota, you will always get a wrong answer. So make sure you're always comparing the quota, is it higher or lower than the geometric mean? So let's look at the same example, our Interplanetary Federation of Fraternia, using the Huntington-Hill method. So again, everything in the beginning works the same as it did for Jefferson, Adams, and Webster. We find the total population. We find our standard divisor by dividing the total population by the number of seats to be apportioned. Then we find the standard quotas by taking each state's population and dividing by the standard divisor. And so this is where we were at this point. Again, if you want to pause the video, take a couple minutes to make sure that you understand where all these numbers are coming from, feel free, to do so. We're going to go ahead and move on with our Huntington-Hill method. Remember that in order to determine whether or not to award the upper or lower quota with Huntington-Hill, we have to first find the geometric mean. So the geometric mean is going to be the square root of the lower quota times the upper quota. Well, what's the lower quota in this case? 19. What's the upper quota in this case? 20. So the geometric mean is going to be the square root of the product of 19 and 20, which is approximately 19.4936. And we're going to do this same process for all of our standard quotas. So we're going to find the square root of 14 times 15, since that is lower quota times upper quota, and that's approximately 14.4914. For C, it's the square root of 67 times 68, lower quota times upper quota. For D, square root of 26 times 27, lower quota, upper quota. And we can do this same process for E and F as well. So now that we have our geometric means, in order to find our initial apportionment, we have to compare our standard quota to the geometric mean. And we want to know, is the standard quota greater than the geometric mean, or is the standard quota less than the geometric mean? Well, we have 19.95, and we're comparing it to the geometric mean of 19.4. So the 19s are the same, but notice that 9 is greater than 4. Therefore, the standard quota is greater than the geometric mean. For B, the 14s are the same, but 1 is less than 4. So 1 is less than 4 means the standard quota is less than the geometric mean. The 67s are the same, but 7 is greater than 4. So since 7 is greater than 4, the standard quota is greater than the geometric mean. 26 is the same, 2 is less than 4, so this standard quota is less than a geometric mean. 2 is less than 4 here as well, so again it's less than. And 0 is less than 4, so again less than. So we have 2 that were greater than the geometric mean, and we have 4 where the standard quotas were less than the geometric mean. So for A, because the standard quota was greater, we're going to award the upper quota. Because B was the standard quota was less than a geometric mean, we will award the lower quota. For C, we'll award upper, and D, E, and F will all get lower since they were all had standard quotas that are less than the geometric mean. And we can see that our initial apportionment was in fact 175, which is what we were looking for, and therefore we do not need to find a modified divisor. If this number had been too high or too low, then we would have went back, found the modified divisor, and repeated this entire process. So just like with all of them, the Huntington-Hill method does have some attributes. The advantages is it applies the same formula to all states. It is population neutral, meaning it doesn't bias larger or smaller states, and it does not produce any paradoxes. It can violate the quota rule. Both upper and lower quota violations can occur, but they are very rare, and therefore this is the apportionment method that is currently used within our government. Now, obviously, our goal would be to find an ideal apportionment method which would not violate the quota rules, it would not produce any paradoxes, and it would not show any bias. But what we see is that nothing that we have looked at thus far meets all of those requirements. And it turns out that Belinsky and Young had a theorem that they have proven that there is not an apportionment method that exists that does not either violate the quota rule or produce paradoxes, because it is a mathematical impossibility. So based on Belinsky and Young's theory, we won't ever have an apportionment method that can't produce violations or paradoxes. So the Huntington-Hill method is a pretty good choice since it can, but it does so very, very rarely.